Non succede nulla. Non ti mangi.
No. Non c'è nessuno, quindi sto parlando con testa. A parte che perché chiedermi no, meno dell'introduzione, no, introduzione. Però i numeri io non li capisco, non mi una volta è stato bellissimo, ho cominciato a dire tutti i numeri in italiano non parlare inglese. Ma ci deve essere due famiglie.
So I think we can start with the afternoon session. The first talk is by Margherita Gambito. It's about solar physics. The title is The Penumbral Filaments from Photosphere to Chromosphere. Thank you, Margherita.
Okay. So, good afternoon, everyone. And as Giorgio told us, I am a solar physicist, and today I will talk about the penumbral solar filaments. Before showing my results, I want to recall some important things about the solar physics, I mean, the sun and the sunspot. Okay. So, I think that everyone knows that the sun is a star, and the most important thing is that the sun is the unique laboratory where the astrophysicist can study some physical processes that happens not only in the Earth but also in environment astrophysicist. So it's really important to study the sun, and it's really important how the magnetic field evolves in the suns. We can imagine that the sun as an onion, where each peel of the onion is a layer of atmosphere in the sun, and the first atmospheric layer that we can see, we can observe with our telescope, is the photosphere, that is this that we are seeing here from the PSPT, the observatory room. And we see this dark structure that is called the sunspot, but in general active region where there are more complex and there are more sunspots inside one active region. So the sunspots are this, this structure, dark structure in the photosphere, and the most important thing is that the sunspot is the site where there is a strong magnetic field. So we have that this is a black hole, I mean, it's the umbra where there is a lot of magnetic field, and then there is the penumbra where these filaments, bright and dark, are interlaced one to each other, and the magnetic field is less strong respect with the umbra ones. In this sketch, we can see how the magnetic field for the sunspot form, and we see how this bundle of magnetic flux tube emerged for magnetic buoyancy from the convective zone, and when cross the photosphere, the sunspot appear. So, and why the penumbra and the umbra is so dark? So it's because the magnetic fields prevent the going up of the convection, so the heating is suppressed. So here the heat, the sun have a temperature rise 4,000 Kelvin, and here there is 5,000 Kelvin, but in the quiet sun there is 6,000 Kelvin. But how we can study the magnetic field of the sunspot? So everyone knows that spectral lines, when it's under the magnetic field, it's splitted by the Zeeman effect due to the magnetic field. So, but in the sun, I mean, here we can see also these things. So we see along the slit there is the spectrum, and we see that for the quiet sun there is no splitting Zeeman of this line. But when we arrive to the penumbra, we have some splitting Zeeman, and when we cross the umbra, that is the strongest area, we have really splitting Zeeman. But the thing is that the magnetic field is not large enough to produce significant splitting Zeeman that we can observe with our telescope. So we use another technique that is called spectropolarimetry, and we describe the polarized solar radiation with four Stokes parameters that are here. There is an example. Here there is the intensity Q, and U describe the horizontal fields, and V, the Stokes V describe the polarization along the line of sight, so the magnetic field along the line of sight. But okay, we have the four parameters, and then how we can retrieve the really number for the magnetic field. So we use some code that is called the inversion code. There are a lot of code, but in this study I use it the SIR and Nicol code. What is the difference? A code works solving the radiative equation transfer for the light, for the solar light, but these two codes works into different under some assumption. These two codes works into different how to say assumption. So we assumed local thermodynamic equilibrium for the SIR code, and non-local thermodynamic equilibrium for the Nicol code. So we can retrieve the magnetic field from the photosphere with the SIR code, and from the chromosphere with the Nicol code. But I mean, how it works in few words. We have the initial model of atmosphere. Then the code solve the radiative equation and give us the spectral synthesis that is compared with our observation. When the fit is good enough, we have the final atmosphere, that is temperature, gas pressure, density, and so on, that describe this radiation where are forming that spectral points. Now I will talk about my works. So I works on penumbral formation, and I works also in the last year on filament structure. How the penumbra forms? Okay, there is few observations because it's really difficult to observe with high resolution this phenomena. But this study showed that the penumbra forms in sector, and there is some things that we have to know. So the area where there is between the two polarity have this kind of elongated granules. That means that there are a lot of magnetic field that is emerging in this area. And they said that the penumbra cannot form there because it's not quiet and it's not stable. And again, this area where before the penumbra is formed, it's characterized by a flow of opposite seeing respect that then when the sunspot is mature. So this is my PhD work. So I make like a survey on the penumbra formation, and I study 3 different kind of along this process. So this is the high resolution from Ibis Mountain at DST in New Mexico. So this is the core, that is the sunspot without penumbra, and this is the penumbra. And this is from space observation acquired by HMI on Solar Dynamics Observatory. So here we saw what happens. This is the line of sight velocity map, and we see that before the penumbral forming, there is this annular zone where there is this downflow in velocity. And when the penumbra start to form, we see that this flow changes its pattern. Sorry? Okay. Then I'm asking if it's always the penumbra can't form between the two polarities. And in this observation, we saw here this kind of elongated granules that it's like where the penumbra is forming and it's fuzzy convection, granulation. And for the previous author, they say that this should prevent the penumbra formation. But in our observation, we saw the penumbra forms and they grows inside. So it's not true that always the penumbra cannot form in that area. Lastly, I make a statistical study on a sample. Okay, it's not right the word statistical, because in physics statistical means a big data set, but for active region, and when you have to catch the right active region that are forming the penumbra when passed through the solar surface, it's difficult to make a big sample. So I studied 12 active regions with the simplest magnetic configuration, and we found that there is no preferred area where the penumbra start to form, and also all of the cases that we are studied show this counter-reversed flow. Now, this year I studied the filaments. So how are the filaments organized? So here we see the photosphere. So we see the magnetic field inclination, the magnetic field strength from the spacecraft. And we see that in the photosphere there is this kind of spine intraspine structure where there is the filaments can be divided in 3 parts. The body of the filaments is horizontal fields and not strong fields. Then there is the tail and the head of the fields, where we see that the heads have vertical magnetic field with the same polarity of the umbra, and the tail have also vertical field but with opposite polarity. But now the question is how the next layer of atmosphere, so the chromosphere, how the filaments are organized in the same way, or this is only a configuration for the photosphere. So this is the only one observation that we have, and they found that there is this kind of spine intraspine structure in the upper chromosphere, but there is no evidence of this spine intraspine structure in the magnetic field strengths. So what was my work? We acquired from the sunspot, from the biggest sunspot of the cycle, the YRM line and the calcium line. That means from photosphere to the chromosphere, and in particular here we can see how thrown along the line, we can sample different layers in the photosphere and in the chromosphere. So we saw that in the wing we have the upper photosphere, and then when we pass to the chromosphere, to the core of the line, we have the chromosphere. This is the penumbra profiles of the iron and calcium lines, and this is the fitting when I inverted the Stokes profile with the nickel code. So this is the U, Q, U, and V. So you can see that there is strong signal also in the chromosphere. These are the maps of the magnetic field. So they are 3 different layers in the photosphere from the iron line, and 1 in the chromosphere for the calcium line. So we saw in all of the maps this kind of structure that, yes, is not good visible, but it's still there. And also in the chromosphere there is this kind of spine interspine structure. To see better, we can study the parameters the variation of the parameters along 3 arcs, 2 in the inner penumbra and 1 in the outer penumbra. And we saw that there is the same variation of the magnetic field strength and the inclination in all of the arcs. So the penumbra have also in chromosphere this fine interspine structure. Then we see also this kind of behavior. That means that we are seeing that the inclination decreases from the photosphere to the chromosphere, but we are looking the magnetic canopy at different ends. So we can imagine this situation. We see the magnetic field lines in photosphere here, and is more horizontal. Then when we pass to the chromosphere, we are sampling, we are looking at another field lines, and this is more horizontal, more vertical, sorry. So we are like making a tomography of the 2 layers of the photos of the sun. So what are the conclusions? The conclusion is that to know the complete structure of the magnetic field from the photosphere to the agar layer in a sunspot help us to have a constraints on how the magnetic field evolves and changes layer by layer in the sun, and we can do a solar tomography of the magnetic fields, and this helps us to understand explosive phenomena like flare or CME or something like that. So it's really essential to understand how is the magnetic field in the lower layer of the solar atmosphere. Then this spectropolarimetric method will be used with the next generation of the solar telescopes, such as EST and DIGIS. So it's really important to test and understand how we can work with these data sets. So thank you.
Thank you, Margarita, for this interesting talk. There are some questions or curiosity.
Margarita, you showed that we have several observations of the penumbra coming up around the ore, but do we start having any idea of the physics beneath how the penumbra is formed? Because somehow this is linked to the immersion of active regions, which is always pictured out in a very simple way with the omega alpha effect, but we know that that's a very simplistic way to see the phenomenon.
Okay, so concerning the penumbra formation, we have imagined that there is this bundle that is emerging in the solar photosphere, so it's continuing to emerge. But then the sun have a larger magnetic fields on surface, so the magnetic canopy is not only what of the sunspot. So at some point in the chromosphere, in the upper chromospheric layer, we saw that there is this kind of canopy that pushed down again this bundle that is emerging. So at that point formed the penumbra. So you can imagine this like spaghetti that is always vertical, but then at some point there is a force that press and push down the field lines. And then there is this kind of fountain that is the penumbra. So this is the sketch that we made with this observation and the last. But yes, I mean, we don't know if there is other effect like the emerging dipole or the moving magnetic fixture around the sunspot. I mean, there are a lot of things. It's for this reason that I choose the simplest magnetic configuration and so on.
Other questions? If not, thank you again, Margarita. The second talk of this astrophysics session is by Enrique Arruge. It's in the field of AGN. The title is From Radio Quiet to Radio Silent, Radio Force in Low Luminosity AGN.
Okay. So can you hear me? Luca, can I turn off the lights? Okay, so good afternoon. I am Elia Galucci. I'm a second-year PhD student at the National Institute of Astrophysics in Rome, and I'm a part of the joint PhD degree, National Institute of Astrophysics, Sapienza, and the University of Rome Tor Vergata. Today, I will talk about a part of my PhD thesis, which is about a radio characterization of a sample of low luminosity agent. So we will see what are active galactic nuclei. We will see what is radio astronomy about, what are low luminosity AGN, and then I will show you the sample and the results I achieved in my analysis, and then I will try to draw some conclusions. Now, active galactic nuclei are among the most energetic phenomena in the universe, and their physics is essentially ruled by the presence of a supermassive black hole accreting in their centers. And you probably have seen the Event Horizon Telescope image. Actually, this is a map, it is a radio map of the black hole residing in the center of the active galaxy M87. Okay? Matter accreting onto the black hole accretes onto an accretion disk, and if we do the simple assumption that it is geometrically thin and optically thick, then you can find that the accretion flow is relatively efficient. Now this and the footprint of this emission from the accretion disk is in the optical UV spectra of AGN in the form of a big blue bond, which is essentially a convolution of black body spectra at different temperatures. Now these optical UV photons from the accretion disk, they interact with the electrons, hot relativistic electrons residing in a corona. And via inverse Compton scattering, they are energized up to the X-rays. And the result in the X-rays is a power law-like component. Then we have a variety of ejection phenomena, like, for example, jets of particles and radiation. They are highly relativistic and highly collimated on scales from parsecs up to the megaparsecs, in the case of radio galaxies. And here you can see again the M87 jet in 3 bands, in the X-rays, in the optical, and in the radio. But we have also other ejection phenomena on slightly smaller scales, outflows and winds of multi-phase gas. And this gas can be traced through, from radio through the optical up to the X-rays. All these phenomena contribute in various ways to the overall spectral energy distribution of an AGN. One point I would like to stress throughout this talk is that while X-rays observations are useful to trace the accretion physics, radio observations, they are useful to trace the ejection physics, okay? So, considering the accretion physics of an AGN, the picture is a little bit more complicated with respect to the one I have just showed you. Indeed, we can essentially tell between two different modes. A relative mode, in which the accretion flow is indeed relatively efficient, okay? And then we have a jet mode, in which the accretion is geometrically thin, but down to a transition radius, beyond which the accretion flow, it becomes relatively inefficient. Now, the transition between these two regimes should depend on some fundamental quantity of the black hole, like, for example, the accretion rate, but the challenge is to understand which are actually the quantities involved and in which way. So we said that the radio emission is useful to trace the accretion. While in the case of the radio loud class, the radio emission has been identified as coming from a relativistic jet. In the case of the radio quiet AGN, it is still a matter of debate. Radio quiet had 90% of the Europe population, and in these sources, the radio emission may be the result of different physical processes, like, for example, star formation, the activity of a corona, and also winds and jets. Probably less powerful, less collimated, and subrelativistic. Okay. And so the challenge is, again, to understand which is the dominant parameter and why. So let's talk about radio astronomy for a couple of minutes. Radio astronomy is my main tool, okay? And in order to do radio astronomy, you need essentially three ingredients: diffraction and Fourier transform. Indeed, you know that the resolution of a telescope is given by this formula in useful units. This means that if you want a 1 arcsecond resolution at 21 centimeters, which is in the radio, you will need to build a telescope as wide as 42 kilometers. Okay? And at first you are quite worried. You are definitely not going to do radio astronomy, but then you start thinking about it, and then you end up with a solution. And the solution is interferometry. In other words, can we synthesize an aperture of that size with pairs of antennas? The answer is yes. And this is what we call aperture synthesis in radio astronomy. And the basic concept is the following. You have two locations on the Earth, and you have two antennas. You detect the signal coming from a source on the sky. The signal is undergoing a geometric delay. There is a difference in the path. You detect the signal, you correlate it with a correlator, and what you get is the relative phase of the signal. The relative phase of the signal at the two locations is telling you where the radiation from the sky is coming. The amplitude, of course, of the radiation is telling you how much. You can generalize this concept to different antennas, to different pairs of antennas. You do the same thing, and what you get is the correlation of electric field on the Earth. But this is equivalent to the Fourier transform of the brightness distribution on the sky, which is what we're interested in. Okay, so you can essentially move from the UV plane, which is the correlation of the electric field on Earth, to the brightness distribution of the sky by a simple Fourier transform. Okay, this is the 2D Fourier transforms you have to perform. And as I was saying, for each pairs of antennas, what we call a baseline, you detect the signals, you correlate them, you obtain an amplitude and a relative phase. This is what we call a complex visibility. You collect a lot of these quantities and you feel more and more this plane. And if you want to reconstruct the brightness distribution of the sky in order to perform your science, because of these equations, you have to Fourier transform them. Okay, this is more or less radio astronomy in 3 slides. Okay, and radio astronomy, it allows you to perform a lot of funny things. You can resolve the emitting components at the milli-arcsecond resolution. You can study the contribution of star formation. You can spot the presence of outflows and jets, okay, for example, in active galaxies. And you can also pinpoint the very center of an active galaxy, like in the Event Horizon Telescope. Of course, you have to collect a lot of information, spectral index, brightness, temperature, in order to discriminate between thermal and non-thermal relative processes. Another tool since recently are the significant correlations which have been found between the radioluminosity and X-rays, and they seem to be valid for active galaxies as well as black hole X-ray binaries. And this has been interpreted as a common underlying accretion and ejection physics. Okay, so this is the framework in which I study my low luminosity AGN. But what are low luminosity AGN? Well, low luminosity AGN, like hobbits, are not simply scaled down versions, I don't know, of man, of dwarves and elves, but there are intrinsic differences considering the accretion physics and the ejection physics, which make them clearly different with respect to their more luminous companions. Here you can find intuitively that they are low luminosity objects, but I would like you to focus on this plot here. This is a spectral energy distribution for a different class of objects in terms of the Eddington ratio, and I would like you to focus on this pink function. You can see that low Eddington ratios objects, low luminosity objects, they seem to lack a big blue bump. The big blue bump, we said that it is a signature of a relatively efficient accretion disk. The fact that they systematically miss this spectral feature has been interpreted in the sense that they are probably associated with a relatively inefficient accretion disk. Okay. Well, in the radio, they appear compact on scales from arc seconds down to milliarc seconds, but they are often accompanied with jet-like features. And as I was saying before, there exists a significant correlation between the radio and the X-rays luminosity. And this correlation is valid for low luminosity GM as well as low hard state X-ray bias, okay? Suggesting a possible common underlying physics. Now, the step forward in our science we made is summarized in this paper. I suggest you to read, and I can summarize here for you. We consider the 10 faintest members of a sample of 28 Seyfert galaxies. This sample is complete and distance limited. So we are considering the faintest sources among the faintest. Okay. These sources have been undetected or marginally detected in previous surveys, so we are really considering the faintest, and you can appreciate this fact considering the distribution of the Eddington ratio. The Eddington ratio gives you a measure of the luminosity of the object somehow normalized to the black hole mass, and you can see that the average Eddington ratio for our sources is 1 order of magnitude lower with respect to the overall sample. So we are really considering the faintest objects. And since they are the faintest, they require very deep radio observations, okay? So our group asked and obtained 10 hours of observations at the Jansky Very Large Array at 4 radio frequencies in order to have a wide radio coverage. And the A configuration of the VLA guarantees the highest resolution and the highest sensitivity, okay? So we are able to sample at the tens of microyansky per beam sensitivity sub-kiloparsec scales for these objects. And I can show you some results. 6 out of 10 sources have been detected, and this is the morphology of the sources. You can see they are compact on all frequencies, either unresolved or slightly resolved, so they are compact as expected. And the slope, in this case, 4477, the slope is compatible with being optically thin synchrotron emission. And the luminosities, as you can see in arc per seconds, they are really low, 36 in log units. And okay, this is another example, 4639, and also 4698, in which the morphology is compact as before, but the slope is what we call a slightly flat, slightly inverted slope. Now, in these objects, flat, slightly inverted slopes are due to the self-absorbed synchrotron emission as coming from the optically thick base of a jet. However, we cannot be conclusive because it may also be due to, for example, other physical processes like thermal free emission. So we will need other information, which unfortunately is not possible to obtain from such observations. But so for the moment, we can only say that probably these two phenomena are causing this morphology and this spectral index. And in another 2 cases, like for example 3185, we have found a clearly resolved morphology. This is clearly non-compact. This complex morphology at the redshift of the source, this angular scale results in a linear scale, a physical scale of something like 500 parsecs, and it is probably due to star formation. Okay? And in order to investigate this issue, we overlapped our VLA radio maps with QL HST optical images, as there is evidence in literature for let's say, there is evidence for star formation processes spread over the host galaxy scale on a ring-like structure. And here there is a hint of ring-like structure. However, this source is for sure worth of a dedicated study. 4 out of 10 sources have not been detected, and this is one of the most interesting points of the paper, because We have studied them with a very low with a very high sensitivity, and since radio emission is a characteristic of the AGN, here we are facing a really interesting point. Are they radio silent? In that case, it would be a breakthrough, but more probably the emission, the fact is that we have to go deeper. We have to go deeper. We have to perform deeper observations in the radio. The very last, last but not least, I would like you to show the significant correlation we have found between radio and X-rays, and the slope of this correlation is consistent with that found for low hard state X-ray bias. In this case, there could be a common accretion and ejection physics, and both sources would be characterized by a relatively inefficient accretion physics. It is still a matter of debate, this analogy, but this is a good point, to study and to which focus on. And I would like to leave you with my conclusions. Thank you.
Thank you, Elio. There are some questions or curiosities. If no, I have one question, because radio astronomy was my second choice when I did my master thesis. Then I decided to go the subject. What is, with modern techniques, the detectability limit of low luminosity RGB? What? Microphone. Now, yes. With modern techniques, what is the detectability limit of low luminosity AGN in terms of angular resolution and emission?
Well, it depends what is your science goal. Because in terms of the sensitivity, this is the limit. This is Here we are using the VLA, the Jansky VLA. This is one of the I would say the best performances you get in radio astronomy is probably the Jansky VLA, and it is a connected in the JVLA. The antennas, they are connected. And you can reach easily tens of microjansky per beam, and this is essentially your sensitivity. At these levels, you are essentially noise dominated. Okay? If you want to resolve the very inner cores of these objects, you can use very long baseline interferometry. In very long baseline interferometry, you can use antennas in different parts of the Earth, different regions. The antennas are disconnected, and you can reach resolutions of milliarc seconds. But in these low luminosity objects, one problem you may face is that they are extremely faint, and going to the milliarc second scales, what happens is what we call, what we usually say that you resolve out the source, okay? Because you use such a high resolution that essentially all of your flux is spread over the image, and you can essentially see nothing. So you have to understand which is your goal. Here we can say that the resolution was not the main goal, so the sensitivity was not.
Okay. Thank you. If there are no questions, let's thank Irene here. And we go to the next speaker, Andrea. Yes. He will talk about machine learning classification of core collapse supernova gravitational wave signals.
So can you hear me? as you can see, my presentation, it's not empty anymore. And you heard yesterday about machine learning applied to gravitational wave, but on a different kind of source. And today I will speak of an application to core collapse supernova signals. And more specifically, I don't want to go too much into the detail of what a gravitational wave is, because you already know, I guess. And I want to concentrate on an aspect which maybe is new to some of you, even though I think you already heard of machine learning. So machine learning is the field of computer science which deals with the problem, is a computer able to learn pattern in data? The general flow scheme is the following. We have some data which exhibit some features. This might be values in a spectrogram, for instance, or values in a time series. We pass this data to a machine learning algorithm. Okay, and this algorithm gives a prediction, an output, which is compared to some target data in what is called supervised machine learning. And this, there is a feedback mechanism which goes through a cost function. The cost function depends on the problem you're solving. A classification problem, which is a discrete prediction, or a regression problem, which predicts a continuous value. So one of the most famous and talked about machine learning algorithms is our neural networks. And the neural networks are based on an architecture which is called a neuron. The input data I talked about is basically numbers, which are weighted by some internal weights. And we have this weighted sum, which is passed on to a generic function, which is generally nonlinear, and predicts some sort of output. This output is what goes into the cost function, ultimately. So you see that the cost function has a dependency from the weights of the neuron. If you stack many neurons together, you get what is called a layer of a neural network. And if you stack many layers, so feed the outputs from previous layers to the next one, you have new weights over here, and you can have what is called a neural network. The idea is that the different layers learn patterns on different scales, learn different types of patterns inside your data. And this will be more clear in the next slide when I talk about convolutional neural networks. Why neural networks? Because they're very good at making prediction when given large data sets with many examples of data. They are very good to implement on GPUs, since we have lots of matrix multiplications. And then the computational load is concentrated in what is called the training phase. Basically, the phase where we feed the data to our algorithm and tell them if the prediction is right or wrong. The algorithm, through a backpropagation scheme, will correct the internal weights of the model in order to have a better prediction with the next sample. And when we pass all the data to our algorithm and correct the weights, basically through gradients of the cost function with respect to the weights of the different layers, we have what is called a training error. And then again, there are lots of existing deep learning libraries in many languages. So this is another advantage, I guess. So a convolutional neural network takes an image, which is numbers, as I said before. It can be have many, for instance, an RGB image, red, green, blue, and passes what is called a convolution filter, which basically means we do a correlation between this filter, the values in this filter, and our data. As you can see here in this GIF, the output is a number here, and what we can think of is to teach our convolutional neural network to learn the weights with respect to each filter. And this means that basically our algorithm is learning patterns, spatial patterns in our data. So different layers Here we have other things called, for instance, the pooling. Pooling means that we can choose among different types of pooling in this matrix here. For instance, I can take every 2 by 2 square and choose the largest value, or do a mean and do some sort of smoothing on our data. But the idea is that every consecutive convolutional layer will learn patterns on different spatial dimensions. Dimensions. Scales, sorry. Our application is to images and to time series. So time series is 1D convolutional neural network, so just a flattened version of this, and our filter in this case is 1-dimensional. So let's talk about physics now, and the starting point is, in this case, a gravitational wave signal from a supernova. Here you can see 2 polarizations. We used one of the most recent models that we summed over our data, some background data, either real or simulated. And what we obtain here are, for instance, spectrogram images. Here you can see this sort of arch, which is the signal, and here you see just the background noise. And there is some normalization going on, so you see different values from the one you expect. So to make the thing more realistic, we insert the antenna pattern correction of the interferometer, since our interferometer, as you probably heard yesterday, is sensible in different ways to different positions in the sky. And this basically gives a factor, a multiplying factor to each polarization between 0 and 1. About the background, we can have the simulated ones, and you see all these smooth curves here, which correspond to the 2 interferometers, which are 3 actually, the Virgo and the 2 lag interferometers, and the future 9 times telescope, which will have a much higher sensitivity, and it's just this guy over here. And we can also use real data, either by Virgo and LIGO, and since all this data is public right here, why not? So this is the pipeline. We have the waveforms, which we filter out at lower frequencies to remove this sort of bump, and add to a simulated noise stream or real data stream. There is some whitening going on here to remove particular lines in our noise curves, and also a detection filter, which is generally based on wavelets. And wavelet values which cross a certain threshold in some wavelet families will produce a so-called trigger. But this can be either noise or a real signal. We skip on this part because we're working to make it better, but we're interested in seeing how the classification of the machine learning algorithm works. So this is a 2-class classification problem where the output will be signal or just noise. So signal is signal plus noise, actually. You can insert also glitch. Glitches are transient noise, which are typically affecting our detected sensitivity and which are in some way can mimic gravitational wave signals. I don't want to go into the details of the algorithms, but there are many important parameters you can sort of tweak. There is the learning rate, which relates to how we correct the internal weights. So the factor basically by which we are changing the weights every time after a wrong or correct prediction. And the high learning rate means we apply a big correction, and a low one means a lower one. Then there is the batch size, and this is also useful because we are dealing with huge data sets, and we have to load just smaller batches of data, otherwise we fill the memory. And you have, of course, the training epochs, which means basically, yes, we can have lots of training epochs, just show the data a huge number of times, but this means that we will have overfitting. So we will overfit our particular data set. Then there are other important parameters like the number of layers, the number of neurons in each layer, the activation functions. So as you can see, it's sort of a mess to tune this sort of algorithms. But let's go into an example of prediction. So this is a two-class problem. We use the video simulated noise curve. And in this particular case, since it's a one interferometer example, we use only very close signals, only up to 1 kiloparsec, so it's less, obviously, it's even less than 1/10 of the galaxy, and galaxy diameter. And we distribute the signals uniformly around the sky, and also this is sort of a not really physical situation, since we have to take into account the disk and everything. And but the interesting part is the classification, which is described here in the confusion matrices. On the y-axis, we have the predictions, and on the on the x-axis, we have the real classes. So basically, everything you see on the magenta diagonals is good, and everything you see here is misclassified. So for instance, all you see here is the fraction, so 0.9 about, of real signals which have been classified as real signals by our model. In these cases, we used a data set containing only one of the two models, and while on this case on the right, we use a data set with both models. So we do a mixed training, and we ask our algorithm only to predict if we are seeing just noise or signal plus noise. And you see that the behavior is kind of similar. So even when you introduce two different models, you can extend to recognize the different models, and this is interesting. You can train the model to the machine learning algorithm to distinguish even between the two models, even though they are similar in the time frequency domain. And I can show here, just jump a little, and these are the two model spectrograms. There is some difference in the time series, and since we're analyzing the time series here, yes. This is sort of understandable. Specifically, the two signals have shorter durations. Now, just to show what misclassification might be, here on the right, on the left, there is a signal, and here on the right, there is no signal. By eye, I would never be able to tell that there is a signal here. And our algorithm, the same. So, interesting plot like this one, that the misclassified signals have follow the antenna pattern function very well. So here you have the square sum of the two values, each between 0 and 1. And you see that more distant signals generally are misclassified more, even with higher values of the antenna pattern function. I think I will skip on this because it's basically the same plot just for the other model. Here you can see an example of the evolution of the loss function. And yes, the same exact plot basically on the other case. I want to stress out that this is done on the two-dimensional data, so on images with respect to the previous one, and with a mixed data set for training. The additional difficulty is that we wanted to simulate the presence of a real trigger, and this means that our images cannot be completely centered. It's too easy for the algorithm to learn just an arch, the arch we showed before, on completely centered in our image. It's more difficult for the algorithm to learn it if we shift the image around a little bit. But we see that actually the accuracies are similar because we have 0.95 and 0.94 for the correct classes here. So this is more or less everything, and I'll leave you with my conclusions. Questions, welcome.
Thank you, Alberto.
have some questions.
Thank you for your interesting presentation. I just wanted to ask, like, which type of linear functions are it? Can you hear me?
Yes.
Okay. Like, what type of non-linear functions did you use? Like, what was your estimates? Like,
What type of non-linear function did you use?
Non-linear function.
Yeah, what type? Yeah.
like it was a sigmoid or like?
Yeah, it's sigmoid. But we also tried with a real function. It's not much cheaper, in fact, here.
Yeah, I know.
So-
I was just curious because like,
Yeah.
I also tried a lot of functions and that's why.
Yeah, you can, depends really on very much on the problems, and it's sort of empirical in some case, but if you go real rectified linear unit or sigmoid, it would be okay generally.
Okay, thanks.
Other questions?
So it was speaking just for the. Okay. Just for the non-experts, he was speaking about this guy over here, which models the nonlinearity network.
And did you try to use recurrent neural networks for the case, the time-related case?
Good question. Yes, recurrent neural networks are, just for the general audience, are a type of neural network which has some sort of internal memories on previous examples. And I've tried to use it in the past for a regression task and thought they were extremely difficult to tune in the hyperparameters, such as the learning rate and everything. So we didn't use this, but recent research points to the fact that 1D convolutional neural networks have, in some cases, similar and even better results. And they have the upside that they are easier to tune. Like you get good results, hopefully, but with less effort. While the recurrent neural networks is, in my experience, is sort of a tough task. But maybe for a classification problem, it will be a little bit easier compared to a regression task, which is more difficult.
Okay, so let's thank again Alberto. We move to the next talk by Rishikesh Pandit about optimizing tomographic clustering for Euclid photometric subtopology.
It's not HDMI, it's VGA. It's VGA.
Is that the man on screen?
VGA. Select VGA. Select again.
Let us see the connection.
Yes. Can you select this over again?
It's working.
Yes.
Yes. Right. Thank you. Sorry for the technical delay. So today I will be talking about a part of my PhD thesis, which I did with my supervisor Enzo Branchini in University of Roma Tre. And this is a part of Euclid consortium, which is the next generation space telescope, which will scan the sky in spectroscopic as well as photometric redshifts for the galaxies up to redshift 2. So we'll get to know about the details of the telescope and the projects later. So this will be the flow of my talk. Most of the things are already covered by Sandeep and Federico as a theoretical background for this topic. And so I will briefly go through it in the first part. Later we will try to see what actually the statistical tools that we are using to extract the clustering information from the data set, and the pipeline building, which is the main part of my PhD thesis, is for this photometric redshift catalogs of galaxies. And then at the end, we will see some results, and then I'll summarize later. So when we say pipeline, the first thing that comes to our mind is our childhood Super Mario pipeline, but this is like a set of codes which are high computing performance codes, which are connected to each other in sets. So that is what we are doing. This is a bit technical, but I have tried to simplify it as much as possible. So we know that our universe is undergoing an accelerated expansion, and we are currently trying to scratch our head and trying to find answer. What is the reason behind it? What is dark matter, dark energy? And the way to answer these questions is we kind of plan the cosmological probes and surveys in a way that we gain the information from them, which when fit with the model the theoretical model, the accuracy of cosmological parameters, when improved, then we will be closer to finding the answers of these big questions in cosmology today. So Euclid is one of the next generation telescope which will perform complementary cosmology probes, which will be for the first time in the observational cosmology. So this is a short introduction to what Euclid will do. It will observe 15,000 square degrees of sky, which is excluding the illuminated part of the sky, which is the galactic plane and the zodiacal light. And then it will be including the cosmological probes, which are like the gravitational lens, the weak lensing part, the baryonic acoustic oscillations, and the redshift space distortions. So we are dealing with the photometric part of the project, and which is expected to observe around 1.5 billion galaxies with their photometric redshift distribution up to redshift equal to 2. And it is expected to also gain significant control over the systematic errors that are there in the experiment. So let's see what is a redshift survey. So this particular survey that we see is a spectroscopic survey where you have accurate estimation of redshift. You scan the spectra of individual objects, and then you estimate with the velocity component, you estimate the distance at which these objects are, and then you try to map them in 3D around us. So this is an example of 3D spectroscopic survey. But on the other hand, the photometric survey is like a fast method of doing of assigning redshift to these objects. And what people do is they have template spectra which they scan the objects with, and they assign the redshifts. So you have higher uncertainty in the case of photometric survey, which is on the left part of this diagram, and this is the spectroscopic. So you can see that the structures are finely resolved, but here you cannot recognize the structures because along the line of sight, the errors are large in terms of photometric redshifts. So these are the main differences, and what we are focusing is the photometric survey. Since it is fast, it will give you the amount of galaxies that you can do cosmology with is around billions, and in the next 10 years the spectroscopic surveys will scan up to 10 billion sources. So it is still like time consuming because you need to scan the spectra of each object individually, but this method is fast, and this provides an extra advantage which can be used as a 3D clustering, but it's analogous to 3D clustering as told in earlier talks before, the tomography, which adds the third dimension. So you have like spherical shells, like 2D shells, which are shown in this schematic. So tomography is in clustering. The tomography is used to have these 2dimensional density fields, which mimic the characteristics of the cosmological field. And the third dimension is the redshift, which is so these shells have some thickness, which is more than the error of the photometric redshifts. And once you have the auto and cross correlations from all these redshift shells, then you have a 3D information, the clustering information, which is lost in the radial direction along the line of sight. So this technique is popularly used for the photometric surveys, but so far we haven't had extensively used it for almost billions of galaxies. So this time in Euclid, this will be used for the full sky galaxy sets. So how do we retain the information from these scanned part of the sky? So this is like the most famous picture in cosmology, the CMB map, where you have anisotropies in some quantity, in this case temperature, but what we measure is the clustering signal. So that is more related to the 2-point statistics, which is related to the position of the object. So most of you are familiar already with the 2-point correlation function, which is the probability of having another object in the vicinity of one particular object, in this case galaxies. So this angular power spectrum is same concept but in Fourier space, and of such maps which are distributed on a spherical volume, the statistics which is extensively used is angular power spectrum, which we will use in this case. And this is how we measure the clustering signal. So this is the angular power spectrum. This is on the y scale is power, and on the x-axis is the multipole. And for those who want to know how they are related, this psi ij is the angular 2-point correlation function, and the CL, this quantity, is the angular power spectrum. So ij means two different redshift shells, and this is kind of cross correlation between these two redshift shells. So this particular delta quantity is a 3-dimensional power spectrum, and this includes if you are computing a power of clustering along the line of sight, you have a window function through which you filter the information, which is this W, and the DNDZ, which is the number of objects observed along the line of sight. So sorry. This is how we retain the clustering information from these maps. And we do this with mock set of catalogs, which are synthetic catalogs produced for gaining the information on the errors that are the error bars and the uncertainties that are on the clustering information. So ideally, people do it with the n-body simulations, but we prefer to choose the log normal method, which is probability distribution defined. It's an exponential Gaussian distribution, which is a fast way of producing these mock catalogs. This is the probability distribution of the in log normal space, and this is the covariance matrix, which has all the information about these errors on these quantities. And the more precise, the more diagonal your covariance matrix becomes, the more accuracy on your parameter increases. So that is the main goal. So let's have a look of what exactly the pipeline is consisting. So we assign the characteristic properties of the density field, and we input it to the codes. And the output that we expect is to have a log normal photo-Z, a synthetic galaxy catalog. So first stage, we create maps using the Flask code, which I will tell you about, and then we add the photo-Z error, which is the Gaussian random error added along the line of sight to the spectroscopic redshifts that are produced by the catalog. And at the last, we enforce some DNDZ, which is DNDZ means number of objects per redshift bin. So you have to assign some selection function so that you get the expected number of galaxies that you expect from a particular survey. So we have tested so far this pipeline, and it works with a full sky case with a galaxy-galaxy clustering information. And let's see how these stages are developed. So first stage, we have input cosmology, which are these are the input power spectrum, again the power on the y scale and the multipole on the x-axis, and then we pour it into the Flask code, which will give out a log normal density field, which is density field map, which then is populated with the MCMC sampling with the number of galaxies in the map. So this is the final output that we get from the Flask. And then we measure the clustering signal using another pseudo CL estimator, which is designed by the UCL team in Manchester and London. And we use this to compute, to estimate the power of the clustering signal. And then we test it with then we verify it with the theoretical signal. And we find that at all stages, we find our estimated results pretty much going with the theory that we expect. So now the second stage is to add the photometric error, this is the photometric distribution, and we slice the photometric redshifts again in redshift bins, and then these are again obtained. So from the photometric space, we again obtain the spectroscopic redshifts so that we can assign some theoretical model to those to the objects in those shells. So we fit it with a Gaussian for the simplicity for the first case, and we find that the model fits better for the spectroscopic case. And for assigning the DNDZ, we try to resample the custom DNDZ, which is a survey-based DNDZ. We resample it with respect to the bin size of the shells that we use, and then we will obtain the theoretical distribution, which is in the spectroscopic space, and then we Monte Carlo reject the objects which are excess in those redshift bins. So for this, we use the top hat filter for the photometric bins. So now we have a full sky sample of galaxies. This will then be fitted on top of it with a binary mask to to mimic the exact same output that will be produced by the Euclid survey. So this is the Euclid mask, which will then will be applied to the obtained catalogs, and then at the end we will try to combine our analysis with the weak lensing, which is the gravitational lensing thing working in the UK. So that will be cross-correlated maps with galaxy and shear fields. So this is basically what my work is. So I would like to summarize with the optimization that we have performed so far in the code is we can produce 1000 mocks in 1 day. So this is really fast, and for the first order statistics, the log normal density fields are fairly accurate to do with your clustering analysis. And at the end, we are trying to make to add some features to the pipeline, which is redshift dependent photo-z error and the window function, which you can modify according to the redshift of the object. And at the end, our goal is to make the covariance matrix of the power spectrum as robust. And let me thank all these people who have helped me with the useful discussions in my team. So thank you so much.
Thank you, Patrick. There are some questions, curiosity.
Yes.
Can you explain a bit more how you added galaxies in your simulations?
Okay. So just go back to this part. So these galaxies have, so you can, you have pixels, the information of each pixel, you have over density. So this is a helix map, and this is basically a Poisson sampling. So this is, in a 3D simulation, you have halos and then you populate halos with the galaxy, but this is like a replica of the sky, which is like pixelated map. So you assign galaxies in each pixel, which is a random process, and this is done with a Poisson distribution in this case. But you can, of course, use any other process with the code.
Okay, there are no other questions. Let's thank again Pandit. Margherita Masano, she will talk about from multi-band observation to the nuclear matter equation of state.
Can you hear me? Okay. In this talk, I'm describing how to constrain the equational state of neutron stars with observation in electromagnetic band of a low matrix binary system and observation in a gravitational wave band with the equivalence of two neutron stars. A neutron star is a compact object that we can model as a sequence of layers of different thickness and composition that surrounding an innermost secret core. There is a quite general consensus of the behavior of matter at the density that are under the nuclear density, so in the external region of the neutron star, while the equational state in the inner core is very uncertain. And this happens for two reasons. First, we lack the experimental data from Earth laboratory that cannot reach the nuclear density, the density above the nuclear density. And second, we are in a non-perturbative QCD regime, so to model the behavior of matter is very difficult. And moreover, depending on the interaction that you assume for the matter in the inner core, there could be the formation of hyperons or a Bose-Einstein condensate or a transition to a new phase where quarks are not confined to nuclei. So to study the relation between the energy density and the pressure in the inner core of the neutron star, we need nuclear physics, because the nuclear physicist has to provide the theoretical model of the equational state, general relativity that give us the theoretical framework to explain and to detect the gravitational wave. From the if you detect the signal emitted from two coalescing neutron stars, you can measure their masses and their Taylor deformability. The Taylor deformability is a parameter that encodes the deformation property of matter and depend on the equational state. Moreover, we need also the contribution from astrophysics, because in astrophysical context, we can measure the mass and the radius of a neutron star in a binary system, and the relation between mass and radius depend on the equational state that you assume. This is a theoretical plot, and each line is obtained by integrating the Thorman-Oppenheimer Volkoff equation that describe the equilibrium configuration of a star in general relativity, and assuming a different equation of state based on the large variety of the equation of state available in literature. For some equation of state, the dependence of the mass on the radius is very steep, in the sense that for different value of the masses, you have about the same values of the radius. While for other equation of state, the dependence is more smooth, in the sense that for different value of mass, you have very different value of the radius. And for the electromagnetic observation, we can measure the mass of pulsars. And in particular, are very interesting the maximum mass measurement for the neutron star. For example, Antonadis et al. Measured a mass for a pulsars of about 2 solar masses, and you can see that each equation state is characterized by a maximum mass. And if your equation state, you are a nuclear physicist and propose an equation state, but your equation state don't reach the maximum mass that we observe, your equation state is ruled out. So in our results, we take into account these results. In April of this year, there is another measurement of maximum mass, but since we require that the maximum mass is above the 2 solar masses, our result is compatible with this new measurement. We need to combine different observables from different bands. So mass and radius for electromagnetic band, and the masses and Taylor deformabilities for the gravitational wave band. Moreover, we need also a method to simply describe the large variety of equation state available in literature. And we can do that assuming a parameterized equation state, in which the equation state is fully specified by a few set of parameters. And moreover, we can also constrain features that may differ from those predicted by current model. And so we can also have index of new physics in this phenomenological approach. There is several representation available in literature focus on the spectral representation. In the spectral representation, the spectral representation is based on the series expansion of the adiabatic index. Indeed, if you integrate the definition of adiabatic index, you obtain the equation state. And the equation state is fully specified by the value of the four parameters of the series expansion. And this parameterization offer accurate fit of theoretical equation state. In particular, when we use the parameterized equation state in the Thorman-Oppenheimer Volkoff equation integration, we obtain the same macroscopic observable that has mass, radius, and Taylor deformability as we use the tabulated equation state. So it's very useful because offer a common basis for all our macroscopic observables. Now we want to reconstruct the posterior probability distribution of the parameter given the data that in our case are the macroscopic observable. And we can do that in a Bayesian approach. where the posterior probability distribution is proportional to a prior information of the parameter times the likelihood function. And maybe you heard about the multi-messenger astronomy in another context with respect to that, because usually for multi-messenger astronomy, you means the gravitational wave observation of the two coalescing neutron star combining with the gamma ray burst, the electromagnetic counterpart, the so-called kilonova. But in this work, we combine the gravitational wave measurement of the two coalescing neutron star with the electromagnetic measurement of low mass 6 binary systems that are completely independent from the gravitational wave measurement in a completely different astrophysical environment. And from the statistical point of view, it is very interesting. Indeed, if you have a neutron star in a binary system that create matter, you can model the flux that detected with satellite and reconstruct the mass and the radius of the neutron star in the binary system. So, we sampled the probability distribution of the parameter of the equational state with a Markov chain Monte Carlo simulation. And in the likelihood, we insert the data from the gravitational wave band from LIGO and Virgo collaboration, and the data from first a set of electromagnetic measurement from Ozer and collaborator that are focused on the thermonuclear type 1 thermonuclear burst. And then we use this Natilia measurement also to compare the results using different likelihood from the electromagnetic band. LIGO and Virgo collaboration measured for the first time the data deformability of a star, that is this parameter that encodes property of matter. And the results exclude some equational state that give us less compact star. We can define the compactness parameter as the ratio between the mass and the radius of a neutron star geometric unit, so it is adimensional. And the results of LIGO and Virgo collaboration support the idea that the equational state has to provide more compact star. And in particular, they estimate the masses of the neutron star involved in the coalescence. The heavy one is about 1.5, and the lighter one is about 1.3 solar masses. For the Ozer study, they model the thermonuclear burst that happens when the neutron star create matter, and in some particular condition, there could be a thermonuclear burst, a thermonuclear reaction. And they measure two massive stars. And this is very important because in this way we can sample a region of higher energy density. And the uncertainty on the radius is about 20%. Natilia and collaborator use another model for the thermonuclear burst and obtain this measurement. Note that for this star, we have the uncertainty on the radius that is less than 10%. So we expect to have better constraints with this set of data. Now the results. We measure the spectral parameters of the equational state with the multi-messenger astronomy. So we have combining the LIGO and Virgo measurement of masses and data deformability with the Ozer measurement of masses and radii, we obtain the red dashed line, while combining the LIGO and Virgo collaboration measurement with the Natilia study, we obtain the blue dotted line. And this measure is very important because if you want to simulate the latest spiral phase of the emerging of neutron star, you can extract the parameter from this distribution. And if you're a nuclear physicist, you can fit your equational state with the spectral representation and calculate how much is compatible with this result. So now we have the measure of the spectral parameters, and we want to reconstruct the mass and the radius of the two neutron stars involved in GW17017, the measurement done by LIGO and Virgo collaboration, with this equational state. And these are the results. This is a mass radius diagram, and each black line represents the plot assuming a theoretical equational state. And the red and the green contour plot are the mass and radius probability distribution reconstructed with this analysis. And the blue and the orange combining Lycon and collaboration with Natillia measurement. We can notice that obtain the tidal constraint, assuming a Natillia measurement that had tidal constraints on the radius. And all the, for example, the equational states that are not in this contour plot are excluded by 90% confidence interval from this analysis. Indeed, also Lycon in vitro collaboration exclude, for example, H4. Now we want to compare our results with the results of note that we also obtained comparable mass with the analysis of Lycon in vitro collaboration that are 1.5 and 1.3. So also Lycon in vitro collaboration reconstructed the radii of the two neutron star. I don't have the Lycon in vitro collaboration data, but in the paper they raised the 90% confidence interval for the radius. So we marginalize the previous distribution because mass is comparable and compare the results with those of Lycon in vitro collaboration. And in conclusion, we obtain tidal constraint on the radius in both cases, and in particular, the value of the radius are shifted to smaller radius for radii. So, in conclusion, we combine together the different observable from electromagnetic band and from gravitational wave band. We measure the spectral parameter of the equational state, and our results strengthen the idea that the equational state has to provide a smaller value for the radius for the neutron star. Thank you for attention.
Thank you, Margherita. There are some questions or curiosity about this last topic. I have just a curiosity, because this is not my research field. How is performed the measure of the masses and the tidal deformability during the
Yes. When you detect for detecting a gravitational wave signal, you need the matched filter method. So you have a bank of theoretical model, and when you have an alert of the signal, because the noise is larger than the signal, you compare the detecting signal with your models, and the models that better match with the experimental data provide the measurement of the parameter, because each model depends on the parameters. So you have to do lots of matrix Monte Carlo simulation. You have to use the bias theorem. So you have that your posterior distribution is your measurement, and your likelihood is given the data, so given the signal emitted from the coalescing neutron star, you compare the data with the parameter. So you have a model, you insert the parameter, and when the match is better, you do a measure of the parameter of the neutron star. It's a statistical approach, but it's very strong.
Okay, thank you. No questions? So let's thank Margherita again. We will reconvene here at 16 for the game of talk. Enjoy.
It's coffee time.
Io adesso non lasciare all'interno
Ma stasera vado già da scendere ma che ore chiude?
Verso le 8:30, mi conviene spostarla.
Quindi andare direttamente al ristorante la macchina, guarda lì, me la voglio a casa, a conviene per la mia vita. E i ristorante sono lontani. Poi c'è sempre il guardiano, per cui anche se arrivi alla fine della notte,
Sì,
ti apre. Qui non c'è un guardiano.
qui c'è, ma bisogna chiamarlo appositamente, bisogna avere una motivazione speciale dopo le 9.
Poi è incazzato.
No, incazzato no. Diciamo
Meglio
che se
lasciare-
uno non ha l'autorizzazione di quello.
Capito? Vabbè, allora vado direttamente al ristorante con la macchina.
Sì, quindi.
C'è posto vicino al ristorante?
Sì, si dovrebbe trovare abbastanza semplice.
Sul testo assolutamente sì, la lasciamo aperta.
Senti, la PDF semplice o
No, sì, sono cose che fanno, quindi fatte ovviamente facendo quindi faccio il PDF, mi complementare.
se vuoi, se no proviamo a collegare il computer.
No, mi sembra più semplice.
Ah, Prendo lo shot. La di dietro io, cioè, la guidavo e ieri che scrivi che che eravamo dietro al computer, ci sto a dire cosa succede sta facendo. C'è la faccia di questo, c'è la momento di grande amicizia. Ora ci dobbiamo cominciare. Vuoi aggiungere qualcosa, Carlo?
Sì, ma sono
10?
10.
No, se sento io giusto per una conversazione, se non c'è cosa da là, se non cosa pretendi? Vuoi il gelato? Il gelato? No. Dici non mi aspetto? No, no, dai. Vado?
Aspetta, così faccio l'ultimo.
Fai l'ultimo avviso. Tu poi accendi.
Sì, sì. Buonanotte.
Okay, I see Francesco is more effective than me. Okay, good afternoon, everyone. It's a pleasure today to have the first keynote speaker of this year's event, and he's Massimiliano Lattanzi. He's a researcher of the IMFN at Ferrara, and he's a cosmologist, so will tell us the latest from the cosmos, and in particular, he will discuss with us the present status and challenges in cosmology. So thanks, Massimiliano.
Okay, thanks Marina for the introduction and for the invitation, and thanks also to all the organizers, and thanks to you for being here. So, I mean, before we start the presentation, I was asked by Marina and the others to do a brief recap of my my career, not for the sake of it, but just to give you an insight of some not so young anymore person who is in academia. So I got my PhD in Rome a while ago, and I was a postdoc in Valencia, Oxford, Rome, and finally Ferrara, where at the end I got this permanent position at the IMFN. So it took a while. I mean, I want basically 10 years between the end of my PhD and getting a position. So, I mean, this is something that, I mean, it's not easy, especially in this particular moment, but still I encourage you, I mean, to try that, I mean, to give it a try, at least to some extent, and personal choices probably at some point will kick in. And I want to give you some reason to do that. So I will tell you some, I hope that the reasons will be the presentation itself, in the sense that what's the reason to try to stay in the academia? I think because that's the reason why we're all here now, in the sense that I don't want to sound rhetorical, and that's why I would like that the presentation will speak for that. But I think that what we like to do is to push the boundaries of knowledge, and this is something that we do in science, in academia. I mean, there's no denying about that. And especially cosmology, and speaking about again cosmology because that's what I do, okay? But I think you can say this for many fields of research now. It's really a vibrant scientific enterprise, okay? So, and another, I think, key point of doing research now in cosmology, and in many fields, probably, and not probably, particle physics is the same, they started before us, maybe other fields is a little bit different, is that you have the chance to work in big collaborations that has, of course, pros and cons, that depends on, I mean, what kind of person you are. But I started myself, for example, as basically working in small groups, not really as theorists, but let's say as phenomenologists, and then now I still have that activity going on. I'm also part of collaborations like Planck, and that's a different kind of work, but still it's really nice to think of yourself as being part of a big experiment, and I mean controlling, I mean, or being responsible for a part of the big pipeline that then will lead to the final data. Okay, so these are the things that I think are worth, I mean, for things for which it's worth to be in the academia. So again, I don't want to sound rhetorical. I hope I didn't, but still, I want to convince you with my presentation. So. The topic, I mean, is the present status of our knowledge in cosmology. So yeah, there is this picture that summarizes in a pictorial way what we know or what we think we know about the universe. You can see that many times. So I'll try to be pedagogical here because I mean, many of you are not in cosmology or not even in astrophysics. So we think that the universe started with a phase of very fast exponential expansion, which is called inflation, okay, during which the primordial perturbations that are the seeds for all the structures that you observe in the universe have been generated. And so this phase starts at a very high temperature. Here, at the end of the inflation, I mean, the universe is at a very high temperatures, expands in a non-exponential way after inflation. Then several things happen that are interesting here when the universe is, especially when the universe is around, I mean, a few seconds old. Basically, we start to form nuclei. This is what is called Big Bang nucleosynthesis. Then the other relevant thing that happens in the universe is this, which is the decoupling of matter and radiation. This is basically the transition of the universe from an opaque regime to a transparent regime, which photons can propagate freely. And this happens when the protons and electrons recombine, or combine actually for the first time to form neutral hydrogen. So this is called recombination. And this is where the cosmic microwave background originates from. This happens roughly 400 years after the Big Bang. Then there is a long period called the Dark Ages, in which basically you don't have any light sources in the universe. And then at some point, the first stars start to, I mean, light up, okay, and reionize the universe. And also what happens here is that the small seeds that were produced during inflation grow, and they end up forming the galaxies, you know, the structures that we see today. So we think that we have a pretty good handle on this, and the reason is that we have many observables, okay, like for example, the CMB, which is something that we can observe directly, the pattern of structures that you see here, so the distribution of galaxies in the sky, and also the abundance of light elements that were formed during the Big Bang nucleosynthesis. So all these observations are very coherent, I mean, can be explained in a coherent way by a very simple model. Now let's start with the observables. Actually, we'll mainly concentrate on this observable, which is the CMB. So someone has defined this as the most famous picture in cosmology. Probably, I mean, he was right. And so this is the pattern of fluctuations in the cosmic microwave background. So the cosmic microwave background is the relic radiation that was produced again when the universe became neutral and transparent to radiation, roughly 400,000 years after the Big Bang. So it appears today as a black body radiation with a temperature slightly below 3 Kelvin, and it's extremely uniform across the sky. Still, it's not perfectly uniform, but there's small fluctuations of the order of one part, a few parts in 100,000, and the pattern of these fluctuations encodes a wealth of information about the early universe. Actually, not just the early universe, not just about the universe as it was when the CMB was emitted, but also about the late universe, because this light has to travel to reach us, and it's affected by the characteristics of the late universe, and also has information about the very early universe, in the sense that this pattern here knows about the initial conditions from which these perturbations were generated. Let me give you some numbers. This happens 400,000 years after the Big Bang. The present age of the universe is around 14 billion years. So this is quite early in the history of the universe. Oops, sorry. Now, this radiation has been observed by many experiments, both from space actually, which is the best way to do that. We'll have access to a very wide range of frequencies, and then you can characterize the other components that are in the microwave sky other than the CMB radiation, also from the ground. But from sky we had basically 3 experiments, which are COBE that flew in the late 80s, early 90s, WMAP that flew in the early 2000s, and Planck that was launched in 2009, observed the sky for 4 years, and provides what is today the best and most precise characterization of the field of CMB anisotropies. And so here, for what concerns the present, I will be mainly concerned with the Planck legacy, so with what Planck is telling us about the universe. So the CMB radiation, as I told you, you have these fluctuations that are fluctuations in the intensity of the radiation, from what we call the temperature of the radiation. But another important property is that the CMB field is polarized, and you see this here. So polarization can be split, can be decomposed in 2 components: a curve-like component and a gradient-like component, which are called respectively the B and the component of the field, and that have different properties under parity. And these 2 components are independent, so these 2 maps are basically actually 3 maps, because this one is actually 2 maps. So it has 2 components. So the temperature is the definitive measurement of the CMB anisotropies. The Planck map is the definitive measurement. The reason being that there is an intrinsic limit to the precision with which we can measure the anisotropies, due to the fact that we observe just one universe, and Planck has basically reached that. This is not true for the polarization, for which Planck has only scratched the surface. And in particular, Planck characterizes quite well the grad-like component, even though it can be done much better with a more sensitive instrument that is specifically designed for polarization, that I think that Planck was not. But Planck is nearly blind to the B component, because as we should see, the B component is much weaker than the E component. So this is really something for future experiments, as I will show you at the end of the talk. So we have 3 maps, but these fluctuations are Gaussians. The fluctuations here are Gaussian, or at least are Gaussian to a high degree. They are completely defined by their correlations, by the 2-point correlation function. Since we have 3 maps, we can in principle build 6 correlations, okay? So the temperature, EE, BB, and the 3 cross correlations. But since T and D on one side and B on the other have different properties under parity, if parity is conserved, it's a good symmetry, then TB and DB should be 0. So we have 4 correlations actually, that are non-vanishing among the 6. Then the correlations can be expressed in in harmonic space. So you basically do a Fourier transform on the sphere, and you get these spectra here. So this is the temperature correlation. This is the TE cross correlation. This is the EE correlation, autocorrelation, so this as measured by Planck. I'm not showing the BB because Planck is sensitive to BB only at the very smallest multiples. So the multiple here is basically an inverse angular scale. Okay, so this plot here is showing you the angular correlation at large angles here and at small angles here. There is a fourth spectrum, however, to which I will come back later, which is the power spectrum of the lensing potential. But let's leave this for later. So the CMB. Most of the information in the CMB, most of the shape of the CMB is mostly determined by early universe physics, okay, by physics happening at the time, around the time of CMB, of matter radiation decoupling. So you see that there is a distinct oscillatory pattern, and there is also a plateau at large scale. So the plateau here is reminiscent of the primordial power spectrum. So these are the scales, these are basically the initial conditions, in the sense that these are scales that are so big that they haven't time to evolve until now. Okay, so here we are still seeing basically the initial conditions from which the perturbations evolve from. Then you have this distinct oscillatory pattern that is due to acoustic oscillations in the baryon photon fluid. And this is basically set by the distance that a sound wave could travel in the early universe from the Big Bang until the time of matter radiation decoupling. And this is set basically by many things. This is set by what's the amount of matter versus non-relativistic matter versus relativistic matter that was present in the early universe, because this sets the time that occurs between the Big Bang and matter radiation decoupling. And it also sets, to some extent, the sound speed of acoustic waves in the plasma. So this part of the spectrum is sensitive like to the total amount of matter in the universe, to the total amount of radiation, in the sense of massless particles that was in the early universe, and so on. And then you also see that there is an exponential cutoff here, an exponential damping, and that is due to the fact that the photon mean free path in the plasma is not zero, but has a finite length, and this damps perturbations below some scale. And this is also sensitive to the expansion history of the universe until the time of recombination. And then, since we are seeing all these now, this is also sensitive to how far we are from the time when the matter and radiation decoupled and this radiation was generated. Okay, this was the TT power spectrum. So what about TE and EE? So this is how they look like. You see that there are many orders, quite a few orders of magnitude smaller than TT, so they represent a challenge, with respect to measuring TT. Okay, also because as I told you very quickly, but we also have other things, other components in the microwave sky. We have the so-called foreground, so we don't look just at the CMB. Okay, so we have what other physicists will call, we have backgrounds. Okay, so the point is that TT, is more or less larger than the backgrounds. But here for EE and for TE and EE, we are in a situation in which our signal is smaller than the background, or the foregrounds as we call them. So it's more difficult to extract it in a reliable way. One thing that you might notice here, so these are theoretical spectra, there are no BB spectra. Why? Because here I'm only considering scalar perturbations. So here I'm considering perturbations that are generated by ordinary density fluctuations. And the point is that ordinary density fluctuations, they don't generate any P mode. Okay, so you don't see them in this picture. But, so this is a picture of the perturbations that are produced by tensor modes in the initial power spectrum. So this means basically perturbations not in the density, but in space-time itself. So these are gravitational waves. Okay, so these are fluctuations in the metric. Okay, and they produce this kind of pattern in the T, E, and TE, sorry, TE and E, and most importantly, they also produce a BB pattern in the sky. So looking, as I should tell you again in the last part of the talk, I mean, looking at B modes is really the observational target of many future experiments, because I mean, if we see B modes, okay, we are basically seeing primordial gravitational waves. So gravitational waves that were produced during inflation in an early phase of the history of the universe. You also have some, as I told you, some sensitivity to late universe physics. For example, this bump here is due to the fact that when stars light up very recently, at least on cosmological time scales, the universe gets ionized again, and then you see a distinct signal at the very largest scales that looks like a bump, and it's called the ionization bump. Another effect related to late time physics is the fact that, as I told you, these photons have to travel through matter. I mean, through the matter distribution in the universe. So if they are deflected, you have a gravitational lensing of the photons of the CMB. So this is again a pictorial representation. So this is the usual effect that you have in general relativity. No? So the gravitational potential of matter can deflect light, and you see that if you basically propagate the CMB field through an homogeneous matter distribution, this is what happens, but this is greatly exaggerated. But you see the appearance of this kind of vortices, let's say, and this is also a very distinct pattern, also because if this field was perfectly Gaussian, the processed field becomes non-Gaussian. Okay, so you can look for non-Gaussianity in the field and use these non-Gaussianities to reconstruct the matter distribution along the line of sight. So this means basically reconstructing the integrated gravitational potential along the line of sight, as you see here. So this is how the reconstructed lensing potential looks like projecting in the sky. So this is something that is basically proportional to the distribution of matter in the sky. And this is the power spectrum, so the harmonic transform of the two-point correlation function. And this is important because this is sensitive, again, to the matter distribution in the late universe, so to times that are much closer to us than the time at which the SMB was emitted. So this tells you that the SMB also gives you a handle on the distribution of matter. Of course, you also have a more direct way to observe the distribution of matter, and it's look for large-scale structures and look for the distribution of galaxies in the universe, and you can use this to reconstruct the matter power spectrum, so again, the Fourier transform in this case of the two-point correlation function, and this also gives you information about the expansion history of the universe, as well as on the characteristics, on the amount of matter, for example, that is present in the universe, and so on. So there is lots of information that are included in the full power spectrum. The only, unfortunately, this is more affected by systematics than CMBEs. And you have mainly two kinds of systematics. One is that when you go to very small scales, non-linearities start to kick off, to kick in. The point is that I didn't say that one good thing about the CMB is that basically all of the evolution of the CMB is linear. Okay, so it's very easy to have a theoretical prediction given a model, in the sense that you have just to solve a system of linear equations. Okay. Here you have non-linearities, then you have to resort basically to numerical simulations, to embody simulations. The other problem with the large-scale structures that somehow limits the power of this probe is that you only observe luminous matter. I mean, most of the time you only observe luminous matter, but you are interested in reconstructing the distribution of the whole matter. Okay, and this introduces a systematic which is called the bias, okay, in your measurement. But one good thing is that there is one information that is encoded here. There is a characteristic scale that is related basically to the, let's say, to the average distance between galaxies, which is a distinct scale that appears as a peak in the two-point correlation function. That means that this is a when you go to Fourier space, this becomes a series of oscillations. And these are called baryon-acoustic oscillations. And they, being a characteristic scale, they give you a handle on the expansion history of the universe. And they are not affected basically by the systematics like bias and non-linearity. So, I mean, they live at linear scales. So these are the observables, okay? And not all of them. There are the big bang nucleosynthesis, there are the direct measurements of the upper constant, for example, to which I will come back later, but these are the observables. So what about the model? So we explain all these in terms of a standard model, which is the standard cosmological model that is called lambda CDM, which is the simplest model that can explain present cosmological observations. So this model stems from an assumption, first of all. Let's state that clearly, that is that the universe is spatially homogeneous and isotropic. This is an assumption, even though it's to some extent verified observationally. Then all this is interpreted in a theoretical framework that is made by general relativity and the standard model of particles. So also here, there is nothing particularly exotic. And then you end up that the observations are well explained by a universe that is spatially flat and whose energy density is provided by non-relativistic matter that makes up 25% of the total, which is baryons and some unknown component that is called dark matter, radiation, that is photons and neutrinos, and a cosmological constant-like component that is also called dark energy. And these fluctuations are Gaussian, and they were originated by a adiabatic, and were originated by a nearly scaling value spectrum, in the sense that we have the same amplitude of nearly the same amplitude of fluctuations at all scales at the initial time. And then this means that you only need 6 parameters to describe these. So 3 are related to the matter energy content, 2 are related to the initial conditions of this nearly scaling invariant spectrum, because you just need an amplitude and a slope that should be very close to 0. And then you have a 6th parameter, which is the optical depth of ionization, that tells you when the first stars have started to reionize the universe. So of course, this is a simple model, even though we don't know what that matter and that energy are. Okay, so this is a problem, I mean, to some extent, but still the model is very simple. And again, these are the 6 parameters, okay, that one uses to describe the model. And of course, since we measure the CMB spectra very well, and not all the values of parameters will give you the observed power spectrum, you can use the observations to constrain the value of the parameters. And this is what you get. This is the present status. And you see here, so here I'm showing you the 6 parameters. This is taken by the 2018 Planck parameters paper. So these are the 6 parameters for various combinations of the Planck data. So, I mean, don't focus on a particular column. If you want, this one is the most constraining one that uses the full Planck information plus the information from the DAO. And you see that the parameters are all measured with sub% precision. Okay, with one exception, that is tau, the optical depth to realization. But this really, I mean, this really means that we are doing precision cosmology. Okay? We can measure the parameters at percent precision. Now, there is one thing that you should bear in mind, is that all of these inferences are somehow model dependent, in the sense that we are trying to explain the observation in the framework of a model, okay, which is a well-motivated one, but still it's a model, okay. Then you might ask yourself, how stable are these parameter values when you try to change the model? For example, if you take your dark energy, which is the component that is responsible for the present-day acceleration, if you take the dark energy and you say it's not a cosmological constant, but it's something more complicated with an equation of state parameter different from -1 that is maybe also varying with time, or you take a more complicated shape for the initial power spectrum, or you add other light species other than photons or neutrinos, and then you still end up that the values of the parameters are pretty much stable. In the sense, it's really difficult to motivate, let's say, the need for additional parameters. Okay, really the data as happy, I mean, they are very happy with the 6 base models, with the 6 base parameters, as long as CMB is concerned. Now, so this means that you can also use this data to constrain, I mean, models with additional parameters. Okay, so here there are many of these kind of things that you can do, and of course here I'm showing just a few which are personal favorites. Okay, it's a very biased selection related to what I do. So one thing that I think it's fascinating, also because it tells you how cosmology talks with particle physics, is that you can constrain neutrino masses from cosmology. So this is the 95% and 68% confidence regions from Planck plus possibly other data in the plane of the Hubble constant that tells you the present expansion rate of the universe versus the sum of neutrino masses. And you see that there is clearly an upper limit, okay, on the sum of neutrino masses here. And if you put that in a plot, this is how it will look like. So this is the sum of the masses expressed as a function of the lightest neutrino mass. Okay. So this is a function. I mean, some nu is just a function of m light given oscillation experiment. I mean, given the information that we have from the lab. So these two curves are for the two possibilities for the ordering of neutrino masses, the inverted ordering and normal ordering. And you see, this is what Planck alone tells you, that the sum of the masses should be below 0.24 electron volts. But if you also combine with BAO, with bioacoustic oscillations, you get 0.12. And this is actually far better than what you can do from the laboratory. Okay, laboratory limits, I mean, depends which limits you think of, but I mean, limits from tritium beta decay, okay, which is another way of obtaining limits on the neutrino mass, okay, are more than an order of magnitude worse than this, okay? Actually, nearly 2. There are nearly 2 orders of magnitude worse than this. Now, another fascinating possibility is that if you have additional species, okay, beyond the standard model, they will show up, okay, in the radiation content of the universe if they are light enough. And this is how much, okay, this is a plot that tells you how much a given species will contribute to the density, okay, as a function of the temperature at which this species decouples, I mean, stops interacting with the other particles in the cosmological plasma. So just to, I mean, this one here is how much a standard neutrino contributes, okay? Now, this is something that you can, so since 1 is a standard neutrino, the standard value, of the expected value of this parameter is 3. It's around 3. It's not exactly 3, but I mean, probably this will take us a little bit faster, but it's not important given the current precision of the experiments. So this is again a plot of the allowed region in the N effective, which is again this density in units of standard neutrinos versus H0. And you see that the data, first of all, constrain this parameter at the 10% level, I mean less than 10% level, more 5%, I would say, and also the measurements are perfectly consistent with the standard value of 3. So this is again telling you that the model is working very well, which also might mean that the model is boring. You know? So I let you take your conclusion. So we should see in a moment that maybe it's not so boring, in the sense that it doesn't work so well in all contexts, okay? But to now, really seems that it's working very well. Finally, another thing that I want to show you is inflation, which is the mechanism that generates the primordial perturbations. So here you have the one parameter. So I told you that there are 2 parameters, okay? One is shown here, okay? And this is again the tilt of the primordial spectrum. So I mean, 1 corresponds to a flat spectrum, okay? And this is just how things are defined, okay? So 1 is a flat spectrum, okay? So scale invariance is here, okay? And here there is another parameter that is not the amplitude of the spectrum, but it's a third parameter that you have in models in which you also have primordial gravitational waves, okay? So this is the amplitude in power, I mean the power in primordial gravitational waves. So you see, there are a few interesting things here. One is that scale invariance is ruled out at many sigmas, okay? And this is also very consistent with what we think about inflation. Because inflation, the simplest models of inflation tell us that the spectral index should be very close to 1, but not exactly 1, okay? And this is exactly what we see. And actually, you can make, given a model, you can make a very precise prediction for these numbers. So this is a very powerful way to discriminate between models. The other thing is that the amplitude of gravitational waves is consistent with 0. So don't look at this. I mean, these are theoretical predictions. So the cut ellipses are the observational constraints, okay? And you see that everything is consistent with 0. This means that we don't have any evidence at the moment for the presence of primordial gravitational waves. And that would be a big, that's a big deal. I mean, it would be a big deal to observe. This is called tensor to scalar ratio. It's called R. It would be a big deal to measure a value of R different from 0, because that would mean that we have primordial gravitational waves. And since primordial gravitational waves are an inescapable, or nearly inescapable prediction of inflation, that would be a smoking gun of inflation. So observing R different from 0 at a high significance will really tell us that inflation really did happen. R is also related to this energy scale of inflation, and these limits here imply that inflation took place at an energy scale that is less than roughly 2 in 10 to the 16 GeV. Now, okay, this is what I was referring to when I told you that maybe things are not working so well. Okay, so we also have other probes of delayed universe. So, for example, we can measure through the distance ladder method, we can measure directly the value of the Hubble constant. Okay, so the Hubble constant, the value of the Hubble constant, which is again the present expansion rate of the universe, you can measure it from the CMB, even though it's an indirect measurement, or you can measure in a more direct way by looking at standard candles, basically. So this is what you get. So these are sorry, I swap these two. So I mean, this is what you get from the CMB, okay, which is here in blue. So this is the value that you get, and this is what Rees et al. Get from this direct method. Okay, so you see that there is a big discrepancy that is around 4.4 sigma. Okay, so again, there are a couple of things to remember here. No? One is that the data are completely different, so we are looking at completely different things. One is an early universe probe, another one is a late universe probe. And again, it's completely different kind of observation. So there might be two things. Either there is a systematic in one or maybe in both of the data sets, or there is some physics that tell us that something is happening between the early probes and the late probes that is changing how the universe is evolving, and that we haven't taken into account. And that would be very, very fascinating. So that would mean that there is some new physics, and that this boring maybe lambda CDM model really is not working that well, so it's not that boring anymore. Also, the fact that this is not a systematics, it's also given that by the fact that basically all the early universe probes give the same answer when combined, and all the late universe probes give this other answer here. Okay, so this is really something that we will know in the next years, given the future experiments. Also, gravitational waves might help in this, because I mean, observations of gravitational wave sources, okay, are a way to probe zero, and then will tell us how much, I mean, which one of these two is right. Now, I will go very briefly to the future. How much do I have? I'm done. Okay. Okay, so I can do that. So as I told you, what are people looking for in the future? I would say that the next target is really looking for primordial gravitational waves. So trying to measure this R parameter, okay, and to trying to measure it and show that it's different from 0. So the R is related, as I told you, to the energy scale of inflation. So measuring it will tell us what is the energy scale at which inflation happened. So this will be made by many experiments. There are many experiments that target the B modes, which again are the smoking gun of tensor modes and then of inflation. There are satellites. So one was CORE that has not been funded. It was an ESA satellite, a satellite from the European Space Agency that has not been funded by ESA. But now India is interested in basically reviving it. Okay, so we might hear again about CORE in the future. And there is also another satellite, Lightbird, by JAXA, the Japanese Space Agency, that has just been down-selected. So this means that JAXA said, okay, we are going to do that. So they put money into that, and this is going to be launched at some point, where some point will be in 2027, probably, at least. So, and this is targeted explicitly to measuring the modes. Of course, you can also observe the CMB from the ground, and this is also a big effort that is mainly led by the US. And there are many detectors working now, observatories working now, and there are many stages. So the activity has been divided in stages. That basically means that the number of detectors that you can put in the power plane is getting larger and larger. I mean, at every generation of experiments. So people are looking eagerly to this stage 4, which should basically start soon, which are experiments that can put 500,000 detectors in the focal plane. So that means you are really beating down your noise. You have problems since you are observing from the ground, which is not really ideal, but still you can somehow compensate that with having many detectors. And of course, there is in between, you have balloon-borne experiments that observe from the higher regions of the atmosphere. And for example, we have the LSP, which is an Italian experiment, and SPIDER. And of course, I didn't say, I mean, we also heard a talk about that. I mean, but we also have galaxy surveys like Euclid or LSST, which are going to observe the distribution of galaxies, and they are going to give us information about that. So let me talk a moment about Lightbird, that, as I told you, has been selected just 1 month ago. It's a Japanese mission, but it's a very big European and Italian participation. So these are the specifications of the survey, but I mean, we don't need that. I mean, this is going to be launched again in 2027. So the main target is to measure R. Okay, so Lightbird wants to measure R with a 10 to the minus 3 precision. So this means that if R is of the order of 10 to the minus 3, we will have a detection. If it's smaller than that, we will be able to put an upper limit. Okay, so this is roughly, I mean, more than an order of magnitude better than what we have now. So you see here, so this is the same plot. This time this is in log scale. Okay, so this is if R is here, that means a few in 10 to the minus 3. You see that Lightbird will be able to measure it. If R is 0, it will put an upper limit of the order of 10 to the minus 3. So this is the main target of Lightbird. Lightbird will be also useful for another, again, personal favorite, which is the mass of the neutrinos, because in combination with other experiments, so this is not something that Lightbird can actually do by itself, but you need other experiments, will allow you to measure the mass at 15 milli-electron volt precision, which means a 4 sigma detection of neutrino masses, because we know that the sum of neutrino masses has to be at least 60 milli-electron volts from oscillation experiments. So I'm done. This is my summary, and I hope that I convinced you that cosmology is a science that has reached full maturity. We have precise observations, okay, that are coherently described by a simple model. And then there is strong evidence for this model, and we can also constrain parameters of extension to the model, and this allows us to constrain particle physics, for example, okay, or to constrain inflation. Still, there are tensions between datasets that might hopefully point to non-standard to new physics, and we are looking forward to next generation experiments that will probably tell us something on at least some, if not all, of these issues. Thank you.
Okay, thanks, Massimiliano. Any question, curiosities?
Thank you for the presentation. Can you comment a bit on the curvature of the universe?
Yeah, okay, so the curvature, okay, there is something maybe here in the yeah, here. So Planck measures the curvature in the sense that you can try to fit the data introducing another parameter, so you don't enforce the constraint that the universe has to be flat. Then you have this parameter, you probably know this, but just for the audience, so which is omega k. So omega k equal to 0 means that the universe is partially flat. Okay, larger than 0 means that the universe is negatively curved. Okay, so it has the geometry of a saddle, and omega k negative means that the universe has the geometry of a sphere. So okay, but here I don't have the, okay, here I only have how much the parameters are changing when you open for omega k. So let me tell you that omega k is basically consistent with 0, even though depending on the data that you use, you have a mild detection for positive curvature, but it's, I don't remember the exact number, but it's 1 sigma and something detection. So I don't think that's enough, I mean, to claim that, that we see that the universe is curved. So I mean, I think that this is still, giving us evidence that the flat lambda CDM model can explain the observations. So it would be nice if we, next generation experiments can measure that more precisely and tell us that the universe is not flat. I mean, the universe is certainly not flat in the sense that the flat is just a point in it's zero volume in parameter space, but we don't know how small that is, and so we wait for the next generation experiments.
Thank you.
Any other question?
Thank you. Just a question about the inflation model. You told that actually with next generation experiments we'll be able to even constrain around 0, so even we may have some kind of result that can actually tell us something about R equal to 0 with some confidence interval.
About what? Sorry.
With R, potential density acceleration. But actually, I was wondering. That's just maybe some philosopher point of view.
That's fine.
A provocation. But the problem, in my opinion, and I wonder what is your opinion in this sense, is that we have many models for inflation, and it seems that we cannot actually completely exclude inflation in a way, because we can even have a model that can provide some low value for tensor to scalation. And what is your opinion in this sense? Because we can make all the effort we want trying to constrain R, but we cannot reach, of course, infinite precision, and we are, of course, limited by cosmic variance, so we can actually always be confident with interval with R. So what is your opinion in this sense?
Okay, yeah, great. Interesting question. So thanks for the question. So what he's referring to is the fact that since the R is related back to the, at least in this simplest model, to the scale of inflation. Okay, we really don't know how low this can be. So we might have just a very low scale inflation, not even so low scale. We might have an inflation that is, a few orders of magnitude below that, and then R will be much smaller than what we can measure in this generation of experiments. Okay, then the point is that if we measure R, then we know that inflation, or at least we have a strong evidence that inflation occurred, but we don't measure R. We cannot say that inflation didn't occur. Maybe we can just say inflation was just at low temperature. Okay, and then if we go and increase the precision with which we measure R, we always have this escape route in telling that the escape was very low. I don't remember the exact number, but it can be something like 10 to the minus 14 or something like that. If you take the inflation happening just before BBN, basically, your lowest limit. So what you're telling is that you can falsify inflation, okay? I don't completely agree with that, because I mean, this is not the only prediction that inflation does. There are many other predictions that have been verified, okay, and that if they weren't verified, they would have falsified inflation. So I think that it's kind of a philosophy of science question. No? The point is that when we should stop testing our model, okay, and I think this also depends on what are the alternatives on the market. Okay, so if you don't have any other model that can explain observation so convincingly, okay, then at some point, even if you don't measure R, you accept that this is the best model that describes what happens in the universe, okay, and then you live with that, okay. And of course, it will be much happier if we can measure R, and then we will be basically sure that inflation happened. But if not, yes, I mean, from a strictly philosophical point of view, we cannot really say that inflation didn't happen. But if we don't have any alternatives, I think if you are pragmatic from a practical point of view, really nothing changes. That also is a very personal opinion.
Okay. Okay, we are running a little bit late, but if there is another last question, we will take it. Otherwise, we thank Vasilija again.
Let's start the last section of today, that was the biophysics section. The first speaker is Anna Spigarova from YNFN of Magnaro, and she will talk about cyclotron solid targets preparation for medical radionuclides production in the framework of the YRM project.
Good afternoon, everybody. Thank you for this opportunity to show you the particular aspect I'm working on. I think this presentation will be enough different from almost everything that you have heard before, because I'm working on an extremely multidisciplinary field. I work in the INFN, the same as Massimiliano, but I work in the Laboratorio Nazionale di Legnaro, also known as LUPA. Sorry, turn on the mic. It's there, turn on the mic. No, you're in your pocket. Yeah, it's a different switch. Try again. Speak, do you hear me?
Yes.
Better? Positive. Okay. So, lower arrow. Okay, great. I will start with an overview of the YRM project I'm working on. I will explain you what are the requirements for the cyclotron solid target that I'm working on. And then I will show you the most interesting methods that we have studied in the last years. LARMAT means the Laboratory for the Production of the Radionuclides for Medical Application. The project contains, as you see from the name, both the construction of the laboratory and the R&D on the methods for the production of the radionuclides for medical application. This medical application depends on the type of the physical properties of the radionuclide, and they can be as diagnostics or therapy, or even a combination of both, that is so-called theranostic. The radionuclide is usually used as a radiopharmaceutical, where the radionuclide is labeled to a kind of biologically active molecule. The radionuclides are usually produced either by the nuclear reactors or by the cyclotron accelerators. We are mainly interested in the second aspect. All the story about the R&D on the production of radionuclides for medical application in our laboratory started with the purchase of this extremely powerful high current cyclotron of the best cyclotrons that has been installed in our laboratory in 2015 and has been commissioned in 2017. All the plans of our lab for this machine can be presented as a quarter foil, where the main is the application for the study on of the nuclear physics aspects. Besides that, there are also the additional applications, like the one, the element for the production of radionuclides. At the moment, we are still going on with the construction of the facility. In the last years, we have started building the laboratories. We are installing the beam line dedicated to our project, but it is still not in operation. I hope so much that it will be in order of 2022, but let's say I'm not responsible to give the precise year of the start in the operation. Even if the infrastructure is still not available in our lab, our group is working on a huge number of the projects for the research and development of the production of radionuclides for medical application. All this is thanks to the strong network of collaborations also with the sectors that have already their cyclotrons installed. Here on the example of one of our projects, I want to explain what Laravel Group is working on. The project is called TechNOSP, is devoted to the production of technetium-99m, one of the most used radioisotope in nuclear medicine nowadays, using the cyclotron accelerator. So what we're studying is the way to produce the route in which the radionuclide of interest can be produced, then the methods to produce the target for the cyclotron, the choice of the irradiation conditions appropriate to produce with the radioisotope of interest with the maximum efficiency, the methods to process the targets after irradiation, the separation, radiochemical separation, purification, quality control, and labeling to create the radiopharmaceutical. As I told you, that this is the medicine that you are using. And the recovery of the material of the starting material, that is extremely important in the case when the enriched isotopic materials are used. Besides that, in the collaboration with other institutions, the radionuclide of interest can be tested as for the imaging or even for the therapy, depends on the radionuclide. Besides already using nuclear medicine technetium-99m, we are interested also in R&D on the emerging radioisotopes like the copper-6467, manganese-5251, scandium-47, and zirconium-89. As you guess, the Laravel Group, in order to cover all these aspects, is extremely multidisciplinary, containing the people with the background like physics, chemistry, radiochemistry, and engineering. For the R&D, we are usually used to work with the solid cyclotron targets. The general requirements for the target contain the resistance under the chosen conditions under the beam, the adequate uniformity, the minimization of the impurities in the final product, and in the case of isotopically enriched material, high efficiency of the production of the target. Besides that, for each defined application, there is a set of particular restrictions. For example, the same thickness of the target can be different completely depending on the application. For the cross-section measurement, is required the target of medium thickness. Instead, for the radionuclide production, the target should be extremely thick. The target is a material of the precursor material deposited somehow on the target backing plate that is kept by the by the target station during the radiation and cooled in an appropriate way. The target material is irradiated by the accelerated proton beam at the neutron, but in our case we are dealing mainly with the protons, in order to create through the nuclear reaction the radioisotope of interest. The yield of the radioisotope of interest depends on the proton current that is to be applied. In order to increase up to maximum the yield and the proton current, the higher efficiency of heat dissipation by the target should be used. The standard approach to cool down the target is the cooling from the back by water or directly or indirect in the contact with the cooling chamber and with the front with the helium flow. Here you can see the standard target stations that we have used in our study in two different hospitals that have the cyclotrons of the low energy. The one here is the 16 MeV GeV bit race. The other one here is 19 advanced cyclotrons. Cyclotron. It should be said that in order to guarantee the purity of the final product, the target backing should be chemically inert. In order to increase up to maximum the production of the radionuclide of interest, we have to work on the maximizing of the heat dissipation. This means time to time to work with a particular material, particular techniques for the target preparation, or particular configurations. For this reason, as I told you, we have in our lab the cyclotron with high energy and extremely high current. We are interested to deal with an exotic, non-standard methods for the target preparation. Here I will show you some of them. For example, maybe someone of you know the technique for the deposition called magnetron sputtering. It is well known in research and industry for the deposition of thin films, means of order of several microns. However, as I told you, for the targets for the production of radioisotope, we need much higher thickness. The problem why magnetron sputtering cannot be used for deposition, it cannot be, is not used to deposit the thick films, is the intrinsic stress created in the film during deposition. By manipulating the parameters of deposition, we have found a way to minimize the stress and to deposit the extremely thick films of hundreds of microns of different refractory metals. This allowed us to use it for the preparation of the molybdenum target for technetium-99 and production, yttrium for the target for production of zirconium-89, and also to apply it for very strange particular baking based on the CVDs in the titanium. This approach has been protected by an international partner. The only problem about this deposition technique is that it has really high losses. So if we have to work with an isotopically enriched material, it is not the best way. Searching for the technique fitting for the no, it was video, sorry. Searching for the technique fitting for the low losses deposition approach, I have put my eye on the high energy vibrational powder plating proposed by Isao Sugai for the preparation of the targets for the nuclear physics experiments. Is an electrostatic deposition of the powders simultaneously onto two substrates that are working as the electrons in the deposition, to which the high voltage of order of 10-20 kilowatt is applied. The powders is charged electrostatically and is started to move and started to be implanted onto the substrates. There is something is not working anymore. Already in the work of Sugai, it was declared some kind of thickness limitation that is not favorable for our application. And we are trying to solve this problem by the E-plate INFN project that I'm responsible for, by studying the high energy vibrational powder plating process pushing to the maximum thickness of the deposition. It's only 2 years project, but we have had to start from scratch, creating a new deposition system and finding the conditions for reliable experimenting. The approach that I have proposed to study this process, that is not so known, is an appropriate design of experiment in order to create a mathematical model that is showing the influence on the thickness of the deposition, the following parameters that are the electric field, the geometry of the system, and the properties of the powders, that are powder size and oxidation level. We have already applied it for a set of different shape, size, origin molybdenum powder. This was chosen as a modeling system. And besides that, already we have tested it with the enriched materials of titanium for the request of another elephant project for the cross-section measurements. As you see from here, we have the results with the maximum thickness not so high, however, already order of magnitude higher than the one that was declared in the previous works. I would say that we still don't have the mathematical model that we expect because we did not complete the set of experiments. However, we have the project ongoing. I would like to take into the advantage of the opportunity of the informal approach of this meeting and tell you if someone has competencies on the process modeling from the physical point of view, it can be interesting to discuss the collaboration. The last approach, giving high quality targets with a high efficiency that we want to show is the spark plasma sintering. That is a kind of press sintering technique using simultaneously the Joule heating and the kind of microplasma heating. We don't have the machine for SPS in our lab. For this, we have had to work in a collaboration with a private partner. The approach is in 2 steps. Here you see the preparation of molybdenum target, but the others were made in the same way. Before the preparation of the pellet starting from the powders by hydraulic pressing, and then press sintering and bonding to backing in the second step of the SPS machine. It was used for the preparation of targets of natural and enriched material for the production of technetium-99M, manganese 52, and zirconium-89. All the targets that we have studied have shown an excellent thermomechanical stability under the beam of the low energy medical cyclotron. At the end, I would like to tell you that it's not an easy approach to choose the appropriate technique because each one has its benefits and defects. And in any case, for the choice, it has to be taken into account the restriction for each particular application. And of course, the cost of the production. And thank you for your attention. And I will be happy to answer your questions and curiosities.
Are there questions?
I'm not from this field, but what kind of quantity that you're talking about when you're saying that, okay, few micrometers of thickness of one particular element? Like, I saw like one plot on slide number 30 that's saying 21.6 milligrams per centimeter square. So can you just explain like what exactly that plot is about?
In the
this one.
Okay. In the case of the experiments for nuclear physics, they are more used to measure or to take into account the thickness in the milligrams per square centimeter. Instead, for material science is more used to define the thickness in microns. In case of this type of material, is of order of 20 micron this thickness, if it's what you were asking. Taking into account the density of molybdenum.
The whole cyclotron, the lab that you are going to build, the whole cyclotron process, how much, like for one particular experiment that you do, how much quantity that is that related to the same number of the atom?
This one is what we have reached by by this deposition method.
Okay.
But the final amount depends on the type of application. Means that, for example, for each radioisotope production, you have to define the optimal energy range of the accelerated particle. Starting from that, you define the optimal thickness of the target. It's more related to the aspect of the cross section of the nuclear reaction. And depends on application. For example, for the case of molybdenum used for the production of technetium-99m is of order of 320 micron, the optimal. The thickness that is higher than this one is not useful because after that thickness, the proton is losing the energy up to the moment that is not almost not participating in the nuclear reaction to create more technetium-99m. So it's the aspect of the nuclear cross-section reaction that you are working on.
Are there other questions?
Thank you. Like, have you ever tried the rotational magnetic field in the case of the evaporation, like the quantum evaporation, to get the...
Are you speaking about sputtering now?
Yes, I'm speaking about
rotating magnetic field?
Yes.
No. I have worked only with the standard stable magnetic field, yes.
Okay, and like when you were talking about like the mathematical models, so like you have the data, and from the data you want to build the mathematical model.
Yes.
Okay, thank you.
It is okay. It is a kind of the model taking into account each of the parameters that you are studying.
Yeah.
With the corresponding coefficients and rates.
Mm-hmm. Yeah, so basically you need to build from the results this theory, right? Somehow.
Yes, the better approach is when you define, at least when you don't have the data, it's better that you optimize since the beginning. You define the plane in which the amount of experiment is a minimal that will give you the reliable data to create the model.
Yes. Now it's clear. Okay, thank you.
Are there questions? Not? Thank you very much.
Thank you.
The last speaker of today, that is Nicole De Simoni of University of La Sapienza. She will talk about FRED, a fast model of Monte Carlo code on GPU for quality control in particle therapy.
Can you hear me? Yeah. Right? Okay. Good evening, I am Nicole De Simoni and I'm a PhD student at Sapienza, University of Rome, and I will talk to you about FRED, which is a fast Monte Carlo code on GPU for quality control in particle therapy. What is particle therapy? It's a modern technique of non-invasive radiotherapy, meaning devoted for the treatment of tumors untreatable with surgery or conventional radiotherapy. It uses charged particles, usually protons and carbon ion beams, to release energy to the tumor body, causing the death of the cancer cells.
In fact, the biological damage is related to the release energy, ionization density, and the type of projectile used. And usually we talk about those, the amount of energy released per unit of mass. In this picture, we can see the release dose along the path in the body, in a target, but can be also a human body. And we can see which is the one of the advantages of using particle therapy instead of conventional radiotherapy. While with conventional radiotherapy, we choose photon beams. Here in black, the release of those is almost continuous during all the pattern in the body. For what concerns charged particles, like protons here in blue and carbon ions, the release dose is concentrated in few millimeters, in the so-called Bragg peak. And with the proton beams, we don't have any dose after the Bragg peak. With carbon beams, we have only a small tail after the beam. I will explain better why it happens. And for this reason, it's possible to avoid to release those after the tumors. And it's important, especially when we have important organs close to the tumor, tumors, yes. But usually, tumors are not only a few millimeters. So what happens is that we use a combination of beams, different energies, to release energy to obtain a wider radiation profile that we can see in this picture. And it is called the spread out Bragg peak that we can see here, where the tumor is that part in red. In the right picture, it's possible to see two different treatment plans of the same tumor, but with two different approaches. One with 2 photon beams, combination 2 photon beams, and one with 5 photon beams. It's possible to see, thanks to the color scale, that means the dose released, that when we use protons in this case, it's possible to avoid here those to healthy organs that are close to the tumor. How can we arrive to define this treatment planning? We need to put together information about accelerator parameters, patient data, that usually is a CT, that give information about the matter that the beam will cross in the patient body, and of course the physician prescription, to understand which part is a tumor that we want to eat, which part is healthy organs where we need to avoid a release of those. All this information together make the treatment planning system. In clinical routine, it's used an analytic TPS, so treatment planning system, which is a simplified beam mode interaction using a 3D water equivalent representation of the morphology of the patient. It's used routinely because it's really fast, but sometimes it be less flexible, especially when there are parts of the body where there is a lot of complex variety of density, and we need to use a lot of different fields. And in this case, so in a number of difficult cases, when there is this situation, we use a Monte Carlo treatment planning system, usually Fluka or Topaz. And with them, it's possible to take into account all the details of the interaction of the beam with the body. And so it can be more accurate in this situation, but at the same time, it requires a long time, computational time. So it's impossible to use every day for each patient. And here arrive our code thread, which is a fast Monte Carlo. So it's a mix of the two because it's fast as an analytic treatment planning system, but at the same time can take into account the details in the interaction, the beam body interaction, and we'll see later the performance and why it can be so fast. And the goal is to use a thread as a quality assurance, so to check if the analytic treatment planning system is correct. Why this is important? Because we want to avoid to release those on the organ that surround the tumor. This is an ideal situation where the spread out Bragg peak cover entirely the tumor in green, and the healthy organs has only a small tail who arrive on the organ. The position of this spread out Bragg peak depend on beam energy, the type of projectile, and the matter crossed. If the treatment plane system is not correct, we can have a situation like this in blue, where the spread out drug peak can cover a part of the healthy organ, and the tumor don't have enough dose to kill all the cancer cells. But of course, medicals are take attention to this part, and safety margin is introduced, especially in the part where there is an empty tumor really close, an empty organ really close to the tumor. And we hope with Fred to reduce this safety margin, and maybe one way to reduce it in a really small part, and this way release more dose to the tumor. And okay, so Fred is a fast particle therapy dose evaluator because that's designed to perform fast and accurate calculation of the energy deposition in the patient body during the delivery of the treatment plan. The plan consists of the whole set of beam direction, particle energy, spot shape, and influence produced by the TPS. And here we can see a comparison between TPS realized with Fred and one realized with an analytic one. And we can see that here we have simulated also secondary particles who are more far from the tumors. No? Okay, so it can be more accurate like Monte Carlo, and at the same time fast, because there is a selection of the information that we want to simulate, and for this this reason we arrive to reduce the time up to a factor of 1,000. At the same time, it's possible to run on GPU and not on CPU, and in this way it's possible to have a plane reoptimization in few minutes instead of several hours. In this picture there is comparison between Fluka and the other two Monte Carlo that are used, Giant and Fluka with Fred, and monochromatic beams of protons in water. And here, elastic and inelastic nuclear interaction, whereas with on and switch off, to check each model separately. And the shape is overlap only in the Bragg peak, as we can see in this zoomed box. There is small differences from Fred and the other two Monte Carlo, but the agreement is within 1.5% in this of the Bragg peak value, so it's enough for our representation. No. Okay, but what is really important to check is the lateral dose distribution. In fact, the value in a single box is dependent on the contribution of many thousands of pencil beams closely bundled in the transverse plane. So here we have simulated 150 mel proton beams in liquid water. And here we can see a dosma in a logarithmic scale, so we can see all the secondary particles that are emitted. In the right part, there is a lateral dose line profile at the Bragg peak, so almost here, in a linear and logarithmic scale, with Fluka in dot black line, and with Fred in red line. And there is a good agreement up to 4 orders of magnitude. To make another check of this of the lateral reproduction of details, we have done another test, the field size factor test, which is a technique that allows to directly measure the contribution of long-range lateral tails in the dose distribution. It consists on a box of water where in the middle, the direction of the beam, can be put a dose detector who can move in the direction of the beam, so like here. And then the beam was shaded like in a grid combination, so each point is a different beam with a fixed distance from one beam to another. And every time the size of the grid, so the field size, increases. And so the detector that is in the center of this grid detect directly the dose of the beam with in the direction of the the detector, and then the detector also details of all the other beams. And increasing the size of the fields, or the size of the grid, we can have an amount of which is the part of the dose arrived from the tails. Here is normalized at a field size of 10, and in red we have the simulation of red, with this dot black point are the data measured by this detector. And we can see that the relative error is under the 2%. So we think that there is an excellent reproduction of the nuclear tail. Here are some performances of the performance of thread. This example is about 150 met proton in liquid water target, and is to make the comparison of the time of simulation with Fluka 104 and with thread. With the same hardware, so single CPU core, we see that the primary at 4 seconds that are simulated are the double in thread. And so the time to simulate one primary is the half. And if we use a single GPU card instead of a CPU card, we can arrive at 100K. And arriving using a 4 GPU card, we can have 2,100K. So with a time that is 0.05 microseconds for primary. So with proton beam, we have an excellent performance. Until here, you have noticed that I have talked only about proton beams. This is because now the code has been evaluated with proton beams. But we would like to use thread also for treatment that use carbon ions. In fact, we collaborate with the CNAO, Fondazione CNAO, which use carbon ions and proton beams for the treatment. The problem of carbon ion is that while with the proton beams, we have only the fragmentation of the target, and so the fragment emitted release those really close to the point where they have been emitted. With carbon ions, we have also the fragmentation of the projectile, the carbon. And those fragments can travel around forward in the body and release those also in this tail. That it's a contribution of the dose that we need to take account for a treatment. Actually, currently the algorithms are not considered in the code, but we are working to implement also this part to use thread also for carbon ion treatment. And now I'm using data of the Ganil experiment to develop this model, which give information about energy and angular cross-section of a carbon ion in different tiny targets of energy of 50 and 95 MeV for nucleon and carbon ion. And this is an example of data that we can analyze to realize our model. Are two different fragments that have been emitted in two different setup. The one is with a fixed target, carbon target, and different angles of detection. So here is the helium, and here the lithium. And here we have a fixed angle detection, and the result with different targets. So using with this data, I'm writing this model, but there are some problems because we have only two different energies, 50 MeV for nucleon and 95 MeV for nucleon, and only part of angles for the setup of the experiment. But it's possible to do a scaling of the kinetic energy of fragments emitted by a beam of different energies, and the same for the angle of emission. I have no time to explain this scaling, but if you have a question after, also in the coffee break, I can explain how we've done it. And in future, we hope to use other data from other experiments. In particular, we collaborate with food fragmentation of target. Maybe you have seen this poster that changes A60. This experiment is designed to study enabling interaction fragmentation of a target induced by a proton beams via inverse kinematic approach. But we can use those data in direct cinematic approach. And if someone has other data that can give us, it would be nice. And of course, other experiments will arrive. We will collect data to realize this model. In conclusion, so FRED is used as a research tool at several clinical and research centers in Europe, so with proton beams. Running on GPU hardware, it is possible to rapidly recalculate complete treatment plan in a few minutes. As I said before, with proton, we have excellent performance. We hope to have this performance also with carbon ions. We are working in progress for the implementation of the nuclear model. And so we hope to use it soon as, for proton beams and also for carbon beams. Thank you.
Are there questions? Comments? Francesco? So one is a curiosity. Do you have to take into account potential movements of the patient when doing this, or is the landscape sufficiently large that you don't care?
Okay, now we are working with center who usually treat patients in the head cancers in this part. So they are really fixed on the plan, and so there is no problems with the movement. For example, it would be there will be other problems with tumors in the part where there is a respiration at the staff, and there are other research groups that are working on this, because of course it's a problem to use the same beams also for part where there is a changing of the matter, because where this predator peak appear depend of the matter that's being crossed. If there is movement, change also where arrive the beam. So I'm not sure because I'm not working on this part, but I think that also the margin will be bigger in that part of tumor for obvious reasons.
Just a curiosity, I would like to know if there is any way to measure the dose that is actually given to the portion of the body that we're feeding and compare with the model that you are producing with FRED.
Now we are using the water equivalent target inside the body. It's impossible to detect it. We, in our group, there is also a part who is detecting secondary particles who escape from the body, and there is a connection between those secondary particles with where happened the traffic. So this is a way that is still working, but detect directly the dose to be sure which part is exactly the dose is impossible, because everything inside the body. So we should open the body, and it's not possible. Sometimes we need to remember that we are not working with target, but with humans.
Yeah, but just to have an idea, for example, comparing with imaging techniques in medicine, I don't know.
Yeah, it's
Can you
done.
compare the imaging that you have after the treatment with the dose that you are giving and the model that you have of the dose?
Yeah, of course, we are also looking at that part, the imaging. There are, for now, a lot of the comparison with Fluka, because I've already done all this comparison. And with water equivalent, it's easier to have a quickly check. But there are also comparisons just with imaging and other stuff like this.
Very nice talk and interesting research.
Thank you.
What exactly, like when you split the beam into the grid.
Into
a grid, when you showed in one of the slides.
Okay.
So do you also apply some kind of filter that, no, the next one,
Yeah.
So,
This one.
the one with the,
Okay. This.
no, the next one, where you split the beam in the grid, a square grid.
Okay, yeah.
Yeah. So, like, is there also some kind of filter that you apply for the intensity of the dose that is like targeted on the source? Targeted on the object.
Sorry, can you repeat?
So you split the beam into the grid, if I understand correctly. So you have multiple beams now.
Yeah.
So do you also apply like some kind of filter to reduce the intensity on the outer surface?
Here is done something like what happened when we do a treatment on the patients. So each point of the grid is a different pencil beam with shotting. And in the accelerator part, when we shoot the beam, it's already focusing on the target. So it's the same thing that we do with when there is a patient. In that usually the picture before it's something that is more continuous. Here it's with a fixed distance in between one point to the other, but it's the same concept.
Okay.
I don't know if it was this the question.
Yeah, I mean, my only question is whether you can control the intensity of each small beam or it's just uniform.
Yeah, this is the part of the accelerator that is fixed to be more accurate possible for the treatment of a patient.
Okay. Thanks.
Other questions? Hello, thank you for the presentation. I've got just one question. Why didn't you use the electrons, only photons in the ion?
Why we use once the protons, one carbon ion?
No, why didn't you use the electrons?
But electrons can be used for tumors that are not in the surface because they can travel only a few centimeters, a few millimeters, depending on the energy for the characteristic of the release of those of energy of electrons.
Okay, thank you.
Welcome.
We have not other questions. Thank you again, Nicole. Thank you very much. Tomorrow at 9:30 here. Luca?
Just an announcement. We would like to show to the people that are coming tonight to the social dinner the exact place. Maybe we can come up with a meeting point nearby the metro station Video Quadrato. I don't know who is here and is coming tonight. Can raise the hand. Okay. I will show you now the map so that we can meet at the metro station, and then we can go from there to the restaurant. It's a very small walk, 10 minutes walk, less than 10 minutes. Okay.